So this is one of my favorite chapters, chapter 11, about testing hypotheses. Like we have some ideas, given some data, we come up with a hypothesis, we build a model. Remember that word? We're going to build a model, or somebody gave it to us, which is just a little black box, is telling us like what we believe to be true. A model is something that we could usually simulate. It's a set of assumptions about the data. Like, I don't know, when we were doing this jury trial, like 26% of the jurors were black. Like, that's the model, and that's what people should have been chosen from, right? Right? But we discovered that there was some issues there. So yeah, models are important. We can use them to simulate stuff. And the question is, this model that I've come up with, does it fit the data that I see? Because the model is usually some like simplified version of things, or like what you hope it to be, stuff like that. So yeah, here's kind of how we simulate it. I want to go over this first one, the racial bias in jury panels, with Robert Swain, because that one was a bit simpler than the Alameda County one. I want to go back over that so that I can ask you guys to do stuff along those lines today. All right, so what we did last time was we had there were 100 jurors that day, right, for that trial of this man, and we were able to come up with a probability, little distribution here, of how likely, like in the population of eligible jurors, how likely is it that that juror chosen randomly would be black? That's 26%, and then non-black would be 74%. And we can call sample proportions to get to pick from this distribution. Like, give me all right, with that sample size, and that's the distribution of the population. Like here, it gives you back like, oh, okay, you got, for this random drawing, 13% black people, 87% non-black. Okay, that's how that happened. And we could simulate, because it's 100 jurors, it's very easy, right? We were able to simulate, all right, after this call, how many black jurors were on our sample jury. And it was, in this case, 13, but every time it's random and it changes, just like the first thing. Item 0, after you multiply it by the sample size, or 100. So that was like 19 for that time. If I rerun that, it gives me a different one. And what we did is we made 10,000 simulated juries, right? 10,000 simulated juries of 100 jurors, and we called this function a bunch of times, and we got a list, or an array, right, of all the counts that we saw. How many black people were on imaginary jury number 1, sample jury number 2, respecting our original model that we really were choosing from this exact makeup of a population of jurors and their ethnicities. Okay, so are there any questions about that? Does this code like ring a bell? Does it make sense? Do you see how I'm reading it? Because we're going to do a lot more of that today. I want to make sure we're happy. You can definitely go back to the code from class today when I stop and have you guys try stuff, because that's what I want to do. It's a helpful thing for the midterm as well, even though this won't be on the midterm. Like, I think stopping and having you try is a really good idea today and next time. So yeah, we did 10,000 trials. We got a bunch of these counts of these imaginary juries, and how many members of it were black given our sample proportions. And yeah, we're able to turn that into a table, into a histogram, and you kind of see that according to our model, of course, it's going to hover around the 27%, or was it 26%? 26% that it was supposed to be. Like, that's what the model is going to give you. Sometimes it's a bit more, sometimes it's a bit less due to chance, because it's 100 people, right? They can be drawn randomly from that population. And then the question was, like, the 8% that we saw in real life, does that fit this model? And we saw that it didn't, right? It never got down to, when we did 10,000 sample juries drawn randomly, we never got down to just 8, right? 8 jurors who were black. We never got above 40 as well, so that's another thing to think about. Like, it's never going to be too big or too small. It's going to hover around that center point there. And we can even count, like, all right, how many times was it 8? How many times was it 8 or less? Because maybe it was even smaller. 0 out of 10,000. 0% times in our samples. So that gives us firepower to say that, oh, okay, that model, this idea that we really were choosing from this kind of population where it was 26% black, 74% non-black, there must have been something wrong with that model. Does that make sense to us? It's coming back. I want to go over this so that we can do it all over again today with new examples. So yeah, that's kind of the setup. And so we noticed that, okay, it seems like this model, even though it's what should have happened in real life, it's not what happened. It's very, very unlikely. It was not likely at all in our example runs. But I guess if you run it like instead of 10,000 times, maybe 10 billion times, you might get some very small number, even smaller numbers and even bigger numbers. But it's just so unlikely that it calls into question the idea that something was fair. Okay, so that's important, and I think that's all that I wanted to review. So does the code make sense with the words attached? Any questions about that before we start new stuff? New examples, at least. All right. So yeah, we also did jury selection, and there was a bunch, and we had a bunch of different kinds of ethnicities, and then we also noticed a problem there. We used a total variation distance there, which was fun. But yeah, I want to zoom on down to a man that you may remember from biology class. So Gregor Mendel created essentially genetics, the field of genetics, like the little Punnett square and all that we did in classes once upon a time. Maybe we're still doing it, depending on our major. So let's remember his experiment. All right, he was working with pea plants, and he noticed something was important about the flower color. All right, so this man grew exactly 929 pea plants. He was very methodical, and he noticed that 705 of those pea plants ended up with purple flowers, very pretty, and the rest were white. So it was purple or white, and the majority, bigger than the majority of them, had purple flowers, and this was that that percentage, right? We can get that started over here too. So this is Mendel. And so he found that, okay, out of 929, there were 705 that were purple. And so we see like a 75.8889% probability, right? That any given pea plant was purple. And so what he thought is, okay, 75.89%, that's a weird looking number. And so he's like, you know what, it's probably likely that there is that's really close to 75%. Maybe there's like a 3 in 4 chance, right? Maybe there's like a 3 in 4 chance that these pea plant flowers happened to be purple. All right, so he made a jump there. He made a guess. It's like, all right, this looks very close to 75%. Maybe it's a little off from 75 due to randomness. See that? So that's kind of neat. And it's like, all right, maybe there's a 75% chance then in real life that the pea plants will have purple flowers, and a 25% chance that they'll be white. Like nature probably likes small fractions. 3/4 chance that there's purple, 1/4 chance that there's white flowers. And then he also said this, it has to do with like fancy probability theory. There's an idea of independence going on. Like regardless of all the colors of the other plants, you use 2 purple pea plant flowers, or you use 2 white pea plant flowers, or you use a purple plant and a white plant. No matter what, it's going to end up with this kind of these kinds of chances. That's what he was saying there. Okay, so that's his model. That's his model. That's what he thought was going to happen. 75% chance we see purple flowers. Okay, so yeah, that's pretty neat, and we can test that. Our goal is to test this, right? We want to see, like, we have his data, like we have the counts of all the pea plant flowers and like what colors they were. We would like to run some simulations to do an actual legitimate test to see, like, is 75% like a good idea? Does that seem right? Okay. Does his model, because his answer was not 75%, right? It wasn't exactly that, but he thought like maybe that was just due to chance. So let's see if that's possible. All right. So we would like to run a test, and in general, like we got a test, and we're trying to pick. We're using that test's results, like we did before, to figure out like, all right, is this way of the world correct, or is this way of the world correct? Does that make sense? That's where we're going. So those different views are called hypotheses. So that's important. We've heard that word before in our lives, I'm sure. And our goal of doing this whole test is like in the end, it will give us which hypothesis is correct. All right. Which one is better supported by the data that we saw. All right. So there's 2 different kinds of hypotheses when we're running a test like this in this class. Maybe we've heard them before if we've taken a statistics class. These may be new ideas. That's okay. They're called the null hypothesis and the alternative hypothesis. Okay. So the null hypothesis, null is like a fancy word. It just means nothing, right? Emptiness, nothing. So the null hypothesis is in like a book, it would define it to be like this: a well-defined chance model about how the data were generated. We can simulate it. Usually, it means like everything was left to chance. There was nothing that wasn't left to chance. Null things left to chance, zero. All right, that's what the null hypothesis means. It's something that we can imagine very easily, usually, and simulate. And then the alternative hypothesis is something that's different. It's kind of the opposite of the null hypothesis. So like we think that the null hypothesis is true, but maybe if our test goes a different way, it will lead us to some alternative. Right? That's a different view about the data. Maybe the pea plants were like they had something different about them. Like it wasn't exactly 75-25 split. All right, that's like an alternative hypothesis, where the null hypothesis was it was exactly a 75-25% split, and the only difference that we had to see, the reason it wasn't exactly that, was due to chance. Okay, those words make a little bit of sense. I'll give you more examples of them, of course, but like that's important. The null hypothesis is some idea that we can simulate very easily. It's like our pie in the sky dream of what might be true. The alternative is something that we'll go to if our model doesn't really work out. Okay. So that's, I guess we could use those in terms of the things we've done before. But here, let's go to this now. Let's see, what do I want to do here? Yeah. Here's what we want. Here's something that we can decide on. Again, you can choose a different number, but we want to like generate a number that will tell us every time we make a little simulation according to our model, whether or not it's like a good, like how, whether or not it's close, our simulation is close to what the model would predict. All right. That's the idea. Okay. So that's a test statistic. That's what we want to generate right now. So that's the statistic that we choose to, when we're simulating, to figure out which of the hypotheses is correct. The null hypothesis, the one that like supports the model, the alternative hypothesis, the one that does not support the model. And so the number that we will come up with is, it's nice that we could have like, again, we only have two options, purple and white. It will do the exact same thing like we did here. It's very helpful like this because we also had black and non-black. We could just pick one and easily get the other by subtracting 100%, right? So that's quite nice. So for Mendel's model, what we'll do is we're going to simulate the distance between purple flowers percentages. So like we're going to simulate, all right, we're gonna simulate growing exactly this many pea plants, 929 of them, and we're gonna count how many were purple, all right? Because we're gonna simulate purple and white flowers, and we can just count the purples because like we can subtract from 929 to get how many white ones there were, all right? So that's quite easy. That's quite nice. And so we'll deal with percentages, and we'll just deal with purple. Why not? All right. So we're gonna get how close was it to the model's prediction of 75% every time we simulate. Okay. That's the goal. If it was really that, sometimes it's going to be a little bit off. How far was it off? We'll take a distance calculation with an absolute value. Okay, so let's get that started at least. All right, so let's see here. How do I want to do that? So, for example, this is what happened. This is like our statistic that we observed in practice. Let's go back to his flowers. So it was 705 out of 929 that he actually grew were purple. All right. So that's 705 out of 929 that he actually grew that were purple. And what we're going to do is to calculate a statistic based on this, like how close was this to 75%? Because it's not exactly, right? It's this. It's not exactly that. What we'll do is this kind of calculation. We're going to get this as a percentage. So that's going to be this times 100, right? So let's do 100 over here. 100 times that. Now it's 75.88%. And then I'll take that and multiply it, or sorry, not multiply it, but subtract 75 from it and see how close that was. All right, so it's like, it's 0.888% away from the model's prediction. Does that make sense? If this was negative, we'd have to also take the absolute value. So let's just like get that ready. Sometimes it's going to be smaller when we simulate. Like that's going to be our statistic that we're choosing, right? That's the number that we're going to calculate every time we make a simulation. Like the number is going to change. It's not 705 anymore, probably. And that's our observed statistic. That's what we saw in the real world. That's what Mendel saw. Observed statistic. Whee. And that is very, very close to 75, but not quite. All right, so that's that number. And yeah, I think that is a good start. So if that's what we're getting, all right, if that's the number we're calculating, we're always trying to see how close was it to Mendel's model, the 75%. Let's pick our null hypotheses and alternative hypotheses. So the null hypothesis in this case is it's really exactly 75% split for purple flowers. 75% purple. Like, that's what it should be. The rest is due to chance, all right? Any differences are due to chance. Due to chance. So that's what the null hypothesis is. Does that make sense? It's like, that's the one the model predicts. Like, exactly 75% of those pea flowers are purple. Any differences that we see in the real world or in a simulation was due to chance. That's the null hypothesis. And then the alternative hypothesis is there's something wrong with the model. The model's not exactly perfect, all right? It's not exactly 75% purple. The differences are not just due to chance. They're due to some other factor, all right? The differences we see are not just due to chance. That's supposed to spell chance. All right. So with those definitions for the null hypothesis and the alternative hypothesis, if this is the number we're calculating every time we simulate a bunch of flowers, how many purple flowers there were, what values of this statistic, the absolute value, simulated purple minus the 75% that it's supposed to predict, the model was meant to predict, what values would support the null hypothesis and what values of that statistic, because it's just a number, right? What values would support the null hypothesis and what values would lean towards the alternative hypothesis, thinking that, all right, maybe it's not 75%, maybe it's something different. Do we have any ideas about that? Any thoughts? What should it be? So we're going to make a bunch of simulations, and we're trying to see how close it was to the 75% here. If our null hypothesis was true, right, and it was exactly 75% purple, I think that it's very, very likely that our simulations will be also very close to 75% purple. Does that make sense? So what will that do to this value if our simulations are very close to 75%? What will it look like? Just numerically. This will be really close to 75, and that's always the number 75. What's 75 minus 75? 0, right? So these values, if the null hypothesis is correct and it really is 75% purple, we're going to simulate that most likely then, if that's true, right? Then we're going to get really, really small values, right? Small distances away from 75%. Does that make sense? Any questions about that? Because we're a little silent today. Maybe it's just because it's Monday. I want to make sure. So that is going to be a very small number. And that's quite nice, right? If it all works out, then we're going to simulate 75 most often. And 75 minus 75 is 0. It's going to be very small. Maybe it's just a little bit away, just like this one. Just a little bit away, right? If the model is correct. But if the model is not correct, that means these simulated values are going to be a little bit bigger or different to 75, right? Could be 65, could be 85, could be something farther away. If we make some simulations, then, and we see that these numbers are large, these distances are large, then that would lean towards the idea of 75% is not the right number. Maybe it was bigger, right? He saw 75, 88, maybe it was supposed to be 76 or something, right? Does that make sense to us? Like maybe that was a bad guess, like it was exactly 75. Okay, so those are the two options, and now our job is to figure out like which one's the right one. Are there any questions about that? This is like new terms, but the same ideas as last time. It's interesting, I think. So yeah, that's what's going on, and yeah, I think what I'd like you to do now is try to take a look at what we did last time for the Robert Swain stuff. Please go to the code from class for last time, because what I want you to do is try to use sample proportions to use Mendel's model. This is our crush dice of the day, our first one at least. Use Mendel's model, which means 75% purple, 25% white, to simulate a garden of exactly as many pea plants as he grew, and 929 of them, of 929 pea plants, and try to extract, right? Extract how many were, or I guess you just want the proportion of purple, right? And extract the proportion that were purple. Does that question make sense to us? You'll go and try to look from last time how we were doing things, because you're going to use the, right, hint, you got to use the sample proportions function. Just kind of like we did here-ish at the very start of the Robert Swain stuff, like these kinds of things. Okay, so please go look there and let me know if you have any questions. But here's the setup, and his. Remember that our model is that we've got 75% purple and 25% white. Purple, 25% white pea plants, and you want to simulate a garden of that many. Okay, extract how many you saw. The proportion that were purple, the percentage that were purple. Okay? Questions about the question before I let you try it? So yeah, go to the code from class from last lecture, because you'll have all the stuff from before at least, and see if you can get this working. So you're going to make a call to sample proportions, right, with exactly 929 things you want to take from, right, because you're trying to pick out pea plants. And then you have to decide on what is the distribution. The distribution that you give to sample proportions is going to be it's going to be what you want to see, right? You got to give an order as well. Like, does purple come first in your call? Does white come first? Because you got to give both, right? Your distribution has to add up to 1, stuff like that. So try to remember that and try to extract the proportion of purple. Okay. And you don't have to submit this answer anyway. I just want you to try and let me know if you have any questions. Like, I want to help. But try to make that simulation if you can. And you better believe where we're going with this is to make 10,000 of those simulations. So if you want to start that, you can try that as well. But I'll bring us back just after this and give you a couple minutes to try. And then when you call sample proportions, it's going to give you back an array, right? An array with a couple things in it, like the proportion that in the sample that were white flowers, the proportion that were purple flowers. If you want to go to a specific piece of that, it's the dot item, right? Dot item 0, 1, 2, 0, 1, 0 the first thing, 1 the second. You know, it's probably easier to look at the code because straight to the code. It's already been done. Yeah, see if you can extract something. Because that's a really good practice for like using arrays, using that sample proportions function. I want to make sure we know what we're doing here. Yeah, I'll give you a few more seconds and I'll show you, and then we'll go from there. Let's solve this then. At least I stopped it then. Nice. So were there any questions about how we were doing this? We'll look at the example from last time. It kind of gives you what we want. But were there any conceptual things that were going wrong as we were trying? Did we get a model? Did we get a sample using the model? Because it's going to look like this. Our sample size is 929, and our eligible population is not population anymore. It's just like proportions of pea plants being purple or white. So it's going to be another array that adds up to 1, but like 1's going to be the purple percentage, so 75%, 0.75, and the other is going to be 0.25, because that's what the model is trying to say, right? And we call sample proportions with those two things. So here, let's think about it that way. So we've got, this is pretty much our proportions, right? This is our distribution according to the model. 75% purple, 25% white. It's going to look like this. It's like a make array of, let's do purple first. You can pick any order you want, purple first or white first, but I'll do purple first. And that will be our distribution, right? That's our Mendel model proportions. We'll say Mendel proportions. So that's what that is. And now I have it. I have it to use. And I can call sample proportions, sample proportions, that function with exactly how many, because I want to simulate, right? Exactly what he did in the real world. Let's see how often it was this far away from exactly 75%, if it really was supposed to be 75%. So sample 9, please grow, simulate growing 929 pea plants with this kind of distribution of purple versus white. And it looks like that's actually good for me, right? It looks like sometimes I'm getting even more. Even if it was exactly 75-25 split, sometimes I'm getting even more purple plants, 76% in this sample drawing. That's helpful. That's firepower towards the null hypothesis. That's great. All right. If I rerun this, of course, it's different. Now it's 7524, so it's a little bit less than he saw there, closer to 75%, the true 75 if that was what the model was predicting. Does that make sense? Any questions about what we're getting at there? It's like it's really drawn from this distribution. It's not always going to be perfectly 75-25, but randomly it's going to pick with that percentage, and sometimes there'll be a little bit more white plants, like more than 25, less than 25. Sometimes there'll be more or less purple plants as well, and it'll go with the order that you give it. So 75 first meant that purple is the first percentage, and then 25 second means that the white was the second percentage. Does that make sense what we're getting out of here? So if you just want the purple, you do like dot item, right? This gives you an array. You say dot item 0 to get a piece out of that. Does that make sense? So that would be our purple proportion. And I can rerun that a bunch of times, and that's the proportion of purple in this sample drawing, the sample, I don't know, garden of 929 pea plants. Okay? So that's what I want. And yeah. Mendel's original model proportions, that's the 75%, right? So Mendel proportion, we'll use this later. Proportion purple was exactly 75%. Another way to get that, because I know that this is an array, I can go to item 0 of this array. Why not? Item 0. So that's just putting 75% there. No difference. All right, so that's my my drawing, and I can get with dot item 0 out of this how much was purple. And so I kind of want to use this value. There's my proportion of purple. I want to use that value to compute this number. That's the number we've decided on. That's how far it was away, this result, how far away it was from the 75% that we think it should be. All right, so we're going to calculate that with every simulated value. Okay, and so to do that, I guess here, let's do this in like a couple steps. To do that, like here's the actual proportions. I can go in and I can get item 0. That was my sample proportion of purple, right? And then I can take that and run this on it. Right? I can call this what? Oops. Sample proportion of purple is that. And then I can use this number, whatever I got, to calculate this. Oops. So it was, what do I want to calculate? It was the absolute value of, take the thing that we got, the simulated proportion, that is not quite a percentage yet. We got to multiply it by 100, right? So 100 times that. And then we subtract Mendel's 75% model proportion, which I've also saved here. Why not use variables? And that's going to be my number to show how far away this particular, oops, what have I done wrong? 100 times sample proportion purple minus Mendel proportion purple is supposed to be times also 100, huh? Because this is not quite a percentage yet either. Minus 100 times that. There we go. Something like that. So now they're both full percentages between 0 and 100. I'll put some parentheses for fun. Like, all right, this one was 0.29% away. This sample garden was, 0.446% away. All right, and that's the number that we're trying to calculate. How far away was this sample garden from Mendel's model, his ideal? Was it 75%, 25% split exactly? Okay, so yeah, that's what we want. And so we want to essentially run this code a bunch of times and go from there. Okay, so I think the next step then is going to be to make a function that I can call to make this happen a bunch of times. Okay, so I think that would be another place for you to try something. So this is going to be similar again to this thing, this function that we did in Robert Swain, like give me a simulated count. So I'd like you to try, all right? I'd like you to try, please. So crush dice again. What I want you to see here is make a function that you can call without any arguments. Let's call it one simulated distance, because it's a distance calculation. To run one simulation and give me back that distance that I want to calculate. And calculate this distance, all right? Distance from Mendel's model. So it's essentially make a function that you can call as many times as you want that does this, gives that answer back. All right. Every time it's different because we're calling sample proportions a different time. All right. So here's all the relevant code. I'd like you to try to make a function again in the style that we did up here. All right. One simulated count. Go look at that for a second. See if you can make that function. Okay. Questions about the question? Why don't you try? So take a few minutes to try that now. Should be pretty quick. You can just copy and paste if you know what you're doing. So I'll give you a couple minutes to try that. Say def. So definitely have open the stuff from last time, the code from class. We all know where to find that, right? Everybody know where to find the code from class. Make that value. Because it'll be different every time. We see what it did that. One function when it was called immediately with nothing. Give it nothing. Parentheses, parentheses. Run a simulation, give me back this distance that I care about. So essentially take all that and put it in a function somehow. All right, I'm going to stop it before the timer goes up so it doesn't make a very loud noise. All right. So yeah, here's kind of what I would think about. It's like def. I'm going to call it one simulated distance. It's going to take nothing at all, and its job is to do this. More or less. What's the one thing I have forgotten if I just paste it in? There's one thing that's missing right now from the function. It's not going to work right when I call it. Return. Good. Yeah, so this is the value, right? I want to give back this value to whoever calls me. When it's a function, you got to say return for the value you're done with and you want to give back. Good. So now I have a function that I could use very easily in a bigger place. I can call it again. Ooh, that's a big distance. Oh man. Even using the model, you can get a distance that large. That's amazing. Call it again, smaller and smaller. On average, it's going to be close to 0 in theory, right? We'll hope. But maybe it wasn't so far-fetched to think that this really was 75-25 split then. That's given us some firepower. That's good. Let's see how often it got this far away. All right, because that's our goal. It's like, all right, Mendel saw this. It wasn't exactly 75% off. There's a little bit more. The distance was this, 0.888% away. Is that still okay to think that it was truly 75-25 split? How often does that happen using the 75-25 exact split model? All right, because that's what we're dealing with. And so, yeah, I just want to call this a bunch of times, and that's essentially this all over again. So 10,000 is a good number. So you can get pretty accurate there. So I'm going to make a big long simulation. It looks exactly like this again. I'm going to make a big long array of all the different distances. I won't call it counts now. It'll be like distances or something. And I'll call it 10,000 times to get 10,000 different simulated distances away from Mendel's model. And we'll see how often was it as far away as he saw in real life. Because that, like, if it was pretty often that we got that far away, then maybe it's okay, right? It's okay to use that model. Maybe we don't have to reject the null hypothesis. That's a technical term, okay? So let us do exactly that. I'll make a little function here, or I'll make a cell with everything we need. So repetitions, how many times do I want to do something? 10,000 times. It's easy to change that if you just use a variable. And then I'll make an array of distances. I'll start out empty. Distance, if I can spell. Distances is just make an empty array with nothing in it. And then I'm going to have a little loop for I in np.arange. So just give me as many repetitions as I have here in arange repetitions. Go that many times, so it's going to run the body of this for loop 10,000 times, because that's what repetitions is. This will give me back an array from 0 to 900, or 0 to 9,999. I don't really care about that. I just care that it's running it exactly that many times. And every time I'm in this loop, what I want to do is add to my distances. I'm gonna call this function oneSimulated_distance, and take that and add it to the end of my distances array. np.append to the distances array, that one new one that we got here. And this doesn't update the original array, so we have to say, it gives back a new one. Like say that distances is now that. That's what we do. And so after I run this, I will have 10,000 simulated distances in my distances array. Are there any questions about what I've just done? Or the reason why I did it? I want to see how often, because we're simulating according to our model, right? Our 75-25% split model that Mendel thought was true. And we're calculating a number based on that model, like how far away it was from the 75% split. If we just look at the purples, right? Because white is, you can immediately get the white from the purple. So we can just look at one side, that's fine. And we are simulating according to that model and getting the distance that we saw just due to random chance 10,000 times. So we'll see like how often it really was randomly just that far away, that observed statistic distance away. All right, because that's what he saw in real life. Does that make sense? Questions about that? Because that's what's going on. Okay. So the goal now is to like shove this into a table. We can make a little histogram if we want. Let's do all that. So all of our distances, we can make it in a table with a single column. It has a long name, so I'll start a new line. Distance between the sample percentage and 75% exactly, because that's what we're calculating, right? Distance between that and 75 for purple only. And that's what our distances array was giving us. And we can look at that now as a table. Cool. Sometimes it's really small, very close to 0. Sometimes it's kind of big. Okay. It'll never be negative because it's absolute value. And so let's make a little histogram. We'll be like dists now. Dists dot hist. That's kind of fun. And so there's my sample stuff. And it looks like it's usually very close to 0, but sometimes even it's okay for it to be almost 4 away. That's kind of cool. Okay, so here, what we want to show is how often was it just this far away, 0.88, our observed statistic away. So what I'm going to do is I'm going to add some stuff. I'm going to give it a little title to this thing. I won't test you on any of this stuff, but you can mess with the way that the graph looks with this little pie plot PLT stuff. So I'm going to add that real quick. It's like PLT.title, make it pretty, prediction made by the null hypothesis, because that's what we're doing here. We're predicting according to the idea that the null hypothesis was true, because that was like, there was a 75% exactly for the purple plants, and anything else that we saw, any difference was due to just random chance. And I'm going to change the Y limit so I can add a little red dot. Dun, dun, dun. You don't have to know what I'm doing. We had an observed statistic, right? That was this 0.888. That was how far away it was. It's about right here, right? About right here, which that distance happened pretty often, it looks like. That's great. It's great for us. Observed statistic at y equals 0, color, make it red, and make the size 55. That seems right. So there, this is my pretty graph. And so this is the 0.888. This is the distance that we saw in real life. This is the distance that Mendel saw. And this histogram is of all the distances that we've simulated. If it really was a 75% split, 25% split for purple and white flowers, it's not too far-fetched to see this number that he really saw. So it is decently predicted, right, by the model. If it was really just a 75% split and everything else was due to chance, the model is happy with that idea for once. Does that make sense? All the other examples from last time was like, the model was wrong. The thing that we saw was way out here or something. But this time it's like, yeah, 75 seems like it's a good number. It will work. Does that make sense, how we can read that? It's like, okay, yeah, the simulation, it predicted a lot of the time that it was just that far away. That's great. That's quite nice. So what we can do is we can count, right? We can count like how many times, let's see, what do I want to think here? Because we have this distances array, right? We can count how many times was it this far away or or any less, right? Something like that, because that would give us firepower for like the null hypothesis is correct. It's like how often is it that when I look at my distances, how did it compare to the thing that I saw? We've called that observed statistic. That's the 0.88. That's the distance that we saw in the real world. How often was it that it was that, or like any how often was distances that, or I guess bigger, right? You can go in either direction. Like how many times was it here or even farther away? Distances was that greater than or equal to observed statistic. That's a bunch of falses and trues. We can count how many times, right? mp.count non-zero. Count how many times it was this much or even bigger, actually. This much or even bigger. How often was that the case in our simulation? So 5, 4, 3, 4. Out of how many repetitions we did, which was 10,000. So we can divide by repetitions to get a percentage. Repetitions. So it looks like for our simulation, according to our model, where we cared about it was exactly that much. It was always a 75% split. Everything else was due to chance. It looks like about 54-ish% of the time, we got a value that was what Mendel saw or even farther away from what he saw. Does that make sense? So that's firepower saying that, yeah, it's pretty likely that 75 is a good number. Okay? That's quite nice. Are there any questions about that? That is firepower towards finally, the null hypothesis. All right, so what we did, right? Here's what we did. We performed the test. We simulated our little statistic under the null hypothesis. We drew a histogram of what we saw. That was all this. Look at that. Beautiful. Oh no, I got all these windows in weird spots. So that gives us a distribution, an empirical distribution, because we're performing an experiment of the statistic we care about, which is this one, that number that we've decided on. You could have picked a different one as long as you're consistent. And this is always approximate because every time we rerun a simulation, we know, right, we're getting a different value. We get a bunch of different values. It's never the same. It's a randomness. But if we do enough of those, it'll give us a good approximation of like what would have happened in the real world if it really was that 75%, 25% split. All right. And so what we did was we compared the test statistic, the stuff that we saw from Mendel's plants, like this one, observed statistic. That's the distance that he saw, right? We compared that to the distances that we calculated for our empirical distribution, the one that we did due to the model, due to chance, all right, under the null hypothesis. And we figured out that, oh yeah, this is not bad, all right? So it looks like over 54% of the time, over 50% of the time, we'd see a value that far out, even if it was a 75%, 25% split, exactly. Chance would give us that. That's beautiful. And this number, this 5434, it's a percentage. It's called a p-value, with a little dash in between p and value. All right, so that's a fancy number that we care about. It's cute that we get to use p-plants as an example. So it's like a p-value. I don't think it's called it for that reason, but yeah, that's called the observed significance level. All right, so because it's probably not the best idea to be like, we're staring at this like, yeah, seems pretty accurate, right? That doesn't seem very precise at all. So it's better to calculate a number like this than to just like stare at the histogram and be like, yeah, I think that's pretty likely. So that's what we're doing here. All right, so that's what a p-value is. It's like, instead of saying like, oh yeah, it's like way over here, it's in the little tail of the graph, so it's unlikely, or it's like in the body of the graph, so it's not, so it is pretty likely. Instead of saying that, we're going to use the p-value. It's called, it's short for observed significance level. I don't know where the p comes from, I can't remember. But yeah, what your textbook would say about that is like, it's the chance based on the model in our null hypothesis that the test statistic, the thing that we're calculating, will be equal to the observed value, the one that we saw, the 0.888 that Mendel saw, or it's even further in the direction that supports the alternative. All right, so that's what we did. We calculated how often was the distance here or even farther away, because large distances would support the idea that the model was wrong, right? So how often was it here or even further away? What was the percentage chance that that was happening in our sample? So we divide by the repetitions. That's this calculation. And we got like 54%, which is a decently large thing, right? If that number was small, that would say that it was unlikely for that value to be out there or even bigger, right? Because that's what we were doing for these other ones. I was secretly calculating p-values. So for like Robert Swain, look at this. I did this one. How often was it 8 or less? 0% chance. Does that make sense? That was a very small number. That means that our model wasn't predicting that thing very well. That was in favor of the alternative. But for us, this was a large p-value. The model is predicting that it would be that far out, or even farther, actually. So that means we don't want to reject our null hypothesis. We have good support for our null hypothesis, right? So small values would support the alternative, because it was like, it's very unlikely for it to be out there or even further in that direction, okay? So that's how you can interpret those graphs. And people have picked numbers, statisticians have picked numbers like, all right, if your p-value is less than 5%, like it's 5% chance or less that you're in that range of your histogram, that they call that statistically significant. And if it's less than 1%, your p-value is less than 1%, your observed significance level, they call that highly statistically significant. So we have none of that for this one. It's like, all right, our model's a pretty good predictor that that would have been a distance. So I think 75% chance is correct. And like, if you actually do the genetics, I think it really is like, that's how it works. So that's beautiful. That's how it should be. And yeah, if it was a different value, let's say that Mendel, he saw some different observed statistic. Let's say that he saw this, like different observed statistic. If it was like, he saw that his plants were 3.14 away, but he was still like, I think it's still 75%. Like it was I saw 78%, but I think it was still 75%. That's close to something normal than I would think. So if he did that, what would have happened? It would have looked like this. Whee! Dun, 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 that prediction made by that color red. Now it's a different observed statistic. Yeah. So let's say he saw a value like that was 78% or 72% or something for purple plants. But he still was like, yeah, I think it's 75%. I think that was all due to chance. So like he saw some number, some distance out here. If that was true, then we need to see like how often was it due to chance that it was that out there or more. Okay? And so again, we can perform this p-value calculation. How often was it that the distance was that far away from this bigger observed statistic, or even farther? This time, if you saw out there, it was like 78% or something. How often did the model predict that? Like 2% of the time. That's a very small p-value, saying that the model is very unlikely to predict a value that far out. So that means that there's something wrong with the model. And we can lean towards, now that's statistically significant, we can lean towards the alternative hypothesis. Okay? So I said a lot of words, but I hope that the words plus the numbers make sense. Are there any questions about this? Because I think that's the example. That's the full Mendel example for the day. Does it make enough sense what we did? Mendel was like, all right, I see this pattern. I think it's 75%, 25% split, but it's not quite that. What was the likelihood that that was due to chance? That's what we were simulating. All right. Even if it was really that, what was the likelihood that it really was that and was due? The differences that we saw were due to chance. Bless you. So yeah, I think that's what I wanted to say about this example. Are there any questions about it before I go to a different one? I have another one for the day. So yeah, another idea is like you can think of a p-value as like an area. If you've taken a calculus class, it's like how often, like if this is what we saw, pretend the red dot is what we saw. How often, and then like the alternative would be supported if it was less than rather than greater than this time. So you can think about like how often was it this or anything smaller that would cause me to think a different way, that the model was wrong. You'd kind of be counting how many things you saw, right? It's another idea of counting, if it's like a smooth graph, is taking an area under that curve. If you've taken a calculus class, that would be an integral, right? So that's another thing that you can pretend is true, and that will be true if you go on to further statistics stuff. All right, I think that's what I wanted to say about all that and p-values. So I do have one more example, but we should talk about p-values for a little bit longer because it's a cool idea. It's just like the probability that the model predicted what you saw. All right, if it was small, that means your model was bad. Okay, that's kind of how you think about it. So your p-value is giving you a number that's useful, though. Right? You can still be wrong if you conclude something according to you saw a very small p-value, like you saw that it was 2.74% chance that the model predicted this thing, and you're like, the model is wrong. That's also telling you how often that you're wrong when you do that. All right, at least you're quantifying that you could be wrong. So if, let's say, your model was good, if the null hypothesis was true, right, that means that the model is fine. Model is correct. If that's true, there is a p% chance that you incorrectly said that it was false, right? Because the model is predicting 2.74-ish% of the time, you really do get a number that far out, right? So maybe you just happen to be in a universe where you were that lucky. Does that make sense? And the model really was the model you thought it was, but it was predicting with very unlikely chances what you saw. It's still possible. You have a 2.74% chance that you were wrong in saying that the model was bad, okay? So that's this one, all right? So like if the null hypothesis is true, but your test is in favor of the alternative, like no, that value is way too far out, the model barely ever predicts that, that's a kind of error, right? You're saying that, oh no, something's wrong with my model when really nothing was. So that's interesting, that's something to think about. You could also have the other kind of error. This is when like your test is in favor of the null hypothesis. Like you really do think the model is correct, but really that's wrong. The alternative is actually true. You can get into this area, which is not really something we want to talk about right now in the class. That's a lot more complicated. One way to get around that and make it so that it's very unlikely for you to ever hit this case, this kind of error. This one's due to a p-value. You can't, like, you can control that by saying I will choose the alternative only if the p-value is less than 1%, something like that. For this one, it's like you kind of just do more simulations in a sense. That's kind of how that works. One way to limit it is to use a larger sample size, then it's more unlikely that you'll end up in this kind of situation where you think that the model is correct, but really it's wrong. Okay, so yeah, that's the flip side. You have two kinds of errors. You think that the model is wrong when it's really fine, or you think that the model is fine when it's really wrong. Okay, so this one has to do with p-values. Okay, so this is kind of technical for the day. Are we still okay? Any questions? So if you can formulate a question, do yell at me. But yeah, I have one more example if we are good. I think there's plenty of time for it. So here's my silly example. All right. One last one. It will be very similar to what we did today. And then we'll do a lot of practice next time as well. So let's say, because this is very applicable because we're about to have a midterm, right? And then a week and 2 days. Don't forget. So here's some silly data that was made up by the textbook people. Let's say that we've got some midterm scores in a class, and the midterm was out of 25 points, and we got the data for every student. Right? We got the data of their scores for every student, and the scores were out of 25 points, and this was a giant class. Maybe it was a data science class at Berkeley or something. So at most four-year colleges, when you take a class with a lab in it, the lab sections are separate from the lectures, and they're not even run by the instructor anymore. All right, so that's what you'll look forward to when you get to a four-year college. I know in this class, right, we have lab section like right after the lectures, and it's still I'm in the room. But at most four-year schools, you go to a lab time, it's a different place, and it's run by a teaching assistant. Okay, not by an instructor. They're just the instructor for that little section. Okay, so they're called lab sections, and let's look at some sample data. All right, it's in this data files called scores by section. So this was made up by, I think it was probably just made up numbers, but maybe it was from a real class. I don't know. We'll find out. So it's scores by section in the data folder if you want to go get that and try it out yourself. But it's midterm scores. That's my example. Yeah. So here, let's get them. I'll call them scores. Table.read table, and it's in the data folder, for me at least, called scores by section. So if you want to get that file and read it in, here's what it looks like. It's got a bunch of section numbers and midterms grades. So like each row is a student. So a student in section 1 in the first lab section scored a 22 on their midterm, and it's out of 25. Some student in section 2 scored a 12 on their midterm. Oh no. Some other student in section 2 scored a 23, so they did a lot better. Good for them. So it's just a bunch of scores, and there are a few hundred of them. Okay, so something went wrong with section 3. Section 3 scores were led by some TA, right? They're all led by a different TA. And section 3 did really bad compared to the other sections. And we want to ask the question, like, should we blame the TA? Is it their fault they weren't teaching the students enough in their lab time? Something like that. So that's what we want to discover right now. All right, we'll talk about null and alternative in a second. But here's the data. I want you to try. Here's another Chris Jice example. This is a good practice for the midterm because this will be midterm topics right now. You got a bunch of different values, like a bunch of different students. Like these are a bunch of section 1 students, and there are a couple of section 2 students. There's a bunch of different sections. I think you should get the average midterm score per section right now. All right, see if you can remember how to do that. Get the average midterm scores by section. That will be a table operation. Can you remember which one? So see if you can try that. And then we'll see like how bad was section number 3, because apparently as the professor, if I saw the section 3 scores, oh, it looks a little low compared to everybody else, maybe it's the TA's fault. Try to get the average midterm scores by section after you read in this file, so you like drag it in, get it on the code from class. It's in the data folder. Try that. Good question. Not. It depends. Yeah, it depends where you are right now. That's something I think. If you scroll down the bottom, it's like, no file. Okay. Do you mind if I try typing? Let's see. That would make sense. Like it does think that downloads is the first folder. Oh, but actually, it's in the same. I think it's always relative to where you are. So if this is the file you're working on, it's in the same folder actually. Okay. You're in the downloads folder already. Does that make sense? So I think that's how it works. Let's try. Okay, cool. Nice. You know, see what we did. There's a table operation from a previous chapter, right? And a good practice for the midterm. We'll have a review as well eventually, but this is a good little mini review. So per each section, see if you can get the average midterm score. Because that's what the instructor did apparently, and they're starting to look and see and ask questions. And then there's going to be more than 10 sections. So if you want to see the output, because it's going to compute, right? A big long table, most likely what you choose to do here. You can say .show with nothing to give it, to have it print out the whole darn table for you. .show. Ooh, that was my timer. All right, so which table operation is going to do it for you? Scores dot what? Mean?
Well, I did scores dot column, and then the section column, and then put dot mean at the end.
That would give you the average section number. I don't think that would do anything for you. There's 12 sections, so the average from 1 to 12 is 6, right? That's not really helpful. You could also do the same thing for midterm, but that would give you the average midterm score for every section. So we want to split it by section. What table operation will split? Group. Good. So we want to group our scores. Scores.group by section. And by default, it's going to give you how many were in each section. So like 32 in section 1, 32 in section 2. Sometimes there's more, sometimes there's less. There are only 27 students in section 3. And if you want to see the whole darn thing, you say .show. But we'll do that in a second. So what we wanted to do is group and not do the count, but do the average, mp.average on all those grouped things. And then again, it gives you back the table. Only 10, but there's 12 sections, so you got to say .show to show them all at once. So that's how you get the averages. Does that make sense? Questions about that? So it looks like midterm average for section 3 is pretty darn low compared to the other ones. So, okay, this is probably doctored data, but just like imagine the gasp that you would have as the instructor. Like, oh no, something's going wrong here. That doesn't seem right to me. Then we can also get the counts of all the students in each section by just not giving anything to group. So like by default, it's going to count. So there are 27 students in section 3, right? So it's a small-ish number compared to some of the other sections, but still that average is looking a bit off. Let's see. So, okay, well, let's say that you're the instructor. You see all this. And you go to, I don't know, the TA in charge of like, hey, something's wrong. Did you do a bad job? And the TA is like, no. And so what are your hypotheses? Like the TA could be like, if you just picked any random 27 students, because that's the size of my section, maybe just due to a random chance, I just got a bunch of students who performed poorly on the midterm. That's the defense of the TA, something like that. So like our question is like, how often we just pick some random students out of all of the sections and got a sample section 3, a simulated section 3. How often would we see a student with like in a section with that bad of a score on average? Does that make sense? That question that we would like to ask right now. If I picked a random section 3 with 27 students in it out of all of these midterm grades, like how often would I see an average this bad? Because maybe it was just due to chance. Just you ended up with a bunch of students in a section that looked like that. Oh no, what have I done? Oops. No idea what I just did. Did I delete a thing? I guess I deleted a thing. Can I undo? Yeah, definitely not. Well, that's weird. Let me try to make the... Sorry. I deleted a thing and I can't get it back, apparently. So what we did is we did a crushed ice where we get the average midterm scores by section, and that was essentially this, but with np.average. Boop. And okay, cool. So that's how it was. Nice. Yeah, so that's what we want to say. That's the defense of the TA. So that's our null hypothesis, right? So our model is like, okay, what we saw was due to chance. That's what your null hypothesis is usually going to say. Like that's what we can simulate very easily. Like, all right, the average score of section 3 is no different from a random section of 27 students sampled from the class. Like, they just happened, like the bad performing students all happen to be in one section. All right. The alternative to that is that no, there's something wrong with that particular section. Maybe the TA was doing a bad job. The average score of section 3 is lower than what we would expect from a random section of 27 students. Like, it was not just due to chance. Null hypothesis is usually something involving chance. Alternative is like, it's not just due to chance. There's something other than the randomness causing that average to be different, to be smaller. Does that make sense to us? Any questions about that? So the null hypothesis is always just like something you can simulate, something that could be due to chance. Okay? The alternative is like, oh no, it wasn't just due to chance. So yeah, let's get some numbers and variables real quick. Make it easy on yourselves. Like the section 3 average, we know was exactly this, 13.66, but we can calculate it from this table, right? If we take scores.group by section, we get the average, we get the column called midterm average, or column 1 if you want to do it that way. And then, so that's this column. Oops, I didn't want to do that yet. So like I get this column, and then I can say, give me item, not item 0, 1, 2. There's section 2, or section 3, right? Index 0, 1, 2 is the third thing. So there's that number, and I can shove that into a variable. That's section 3 average, and then same for section 3 size. It's pretty much the same idea. I can get variables. It's very easy to like do this for other sections now. If you do it programmatically like this, put them into variables. Section 3 size is the same idea, but like just get the counts. The column is called count in that case. You can also just say column 1, 0, 1, item 2. So I've got the size and the average tucked away safely. And our goal now is, all right, to simulate this a world under the null hypothesis. Like I'd like to pick out a random section of 27 students from all of the class, from all these grades. So this original scores table, like just get a bunch of random students, right, from everywhere and take their midterm scores. Does that make sense, what I want to do? I want to simulate a random section out of this class. Like, let's pick some random students out of all the students I have here and get their midterm grades, as many as there were in section 3. Okay? So that is what I like to do. And get the average score. Right? So I've got a table called scores. I want you to think about this for a second. I think this would be a good thing to ponder on your end. So try to do that if you can. So you've got this. It's going to be taken from the scores table, but I want you to try to make one simulation of a class of 27 students under the null hypothesis. I'll spell it out really quickly. So example for you to try. I want you to try it. So simulate a section with the same size as section 3, so 27 students, you can use this variable if you want, by picking random students and get, oh goodness, how did I do that? Random students and get the average score. All right. You don't want to, because this is like all the students ever. You want to make a section with 27 different students. So when you're making your sample, don't duplicate them, because by default, there's a thing that you're going to need here, and it's going to duplicate them. So don't allow any students to be included multiple times, because that wouldn't have happened in real life, right? If you're trying to regenerate groups of students here, you have a bunch of students already, pick 27 of them, they're all separate people, right? Don't re-include anybody because you're going to be using scores dot what to get a random simulation of 27 of them. What thing on table will give you, we'll pick out a few rows because each row is a student. Remember the one? Let's go find it. So it's a lot of stuff to keep in your head, I know. But it's going to be advanced table functions. To apply a function, to group things. We know about pivoting. We know about joining to attach things. Dot sample. Dot sample to get a random sample of some rows of a table. All right. And you're going to be messing with this with replacement because by default it's true. And you don't want to replace students. You don't want that at all. All right. So that's my question for you. So you can use scores.sample to get the right size, and that will give you a random section of students of the same size, and try to get the average of the midterm scores for that random sample of, what was it, 27? Yes, 27. Yeah, take a couple minutes to try that. I just want to give you a head start on all these things so you can at least think about them, because this is like dot sample. That's something that I can test you on, right? This kinds of simulations that we're doing in this chapter, I can test you on. That's new stuff. Dot sample. That's the effect. It's going to be simple, but which I can test. And I use the variables if you already typed them out. Because you can type 27 or put 27 if you want to. I forget what else there was. Scores dot sample, and then you might have to look at the documentation for dot sample. So it takes two things, right? One for sure, up to two things. You're going to need both. Can I stop it before the sound? Yes. All right, were we able to get a sample? 27 students with no duplicate students? So I've called this table scores, and I'm going to say scores.sample. And I'm going to sample. You say first how many you want. So I want 27 that I've saved in the section 3 size variable, conveniently. And then I don't want replacement. Because with replacement, it could redraw that same student a couple times, and that would never happen in the real world. So we want like an actual section that we could have actually generated a different section 3 of real students. So the real students are the rows in this table. I don't want to duplicate them. So I say with replacement equals false. And that will give me 27 random students. Some of them were in different sections, right? But all I really care about is their midterm scores. Does that make sense? Like that'll give me a random section. And let's simulate a bunch of different ways that I could have created section 3, because some students are doing better than others, and some of their scores are different. All right, so that's my random section. I'll call it that, random section. And so I'm going to do this 10,000 times, of course, but like, all right, I've got a random 27 students. Let's get their midterm column and take the average, right? Column midterm, and then take the average of this random sample, np.average, or np.mean. two options. And it looks like this average was 14.25, which is pretty small, right? Decently small, but not quite 13.667. Yeah, interesting. So it could be small, just randomly. If you did another sample, you get a different value. And so you better believe we want to try this process a bunch of times because every time it changes. Let's make a bunch of different kinds. Let's simulate our model under the null hypothesis 10,000 times again, and pick a bunch of random section 3 students, take their midterm score average, and see how often is it the case that the scores were this bad. Because if it was pretty often that happened, then it's like it's not the TA's fault. So let's make a function that gives us a simulated average doing this kind of process. So I'll call it def1 simulated average. Let's see, how do I want to do this actually? Is this fine? Or actually, if I want to do it quickly, how did I calculate this? Let's try to do it in one line just for fun. Random section, how did I get a random section? It was this. So you could really do it all in one line if you want to. It's like that entire simulation, I could have it happen in one line. So there's a very well-performing section 3. There's a worse performing one. So like in one line, you can just do it like that. Cool. Nice. So let's do it like that. So I just need a function that returns this value every time I call it. Def1 simulated average. Call it with nothing, and it returns this answer back. So one weird value, right? One simulated value. Boop. And so every time I call it, it gives me a new number. Ooh, this one's pretty small. That was pretty close. So maybe the model does sometimes predict a random section with that bad of a grade. But it looks like most of the time it's not that bad. Okay? So yeah, our goal now is to, a bunch of times, let's see, that can be the last thing I have you try really quick, but let's simulate 10,000 of these one simulated averages, all right? Because we want to see how often is it the case that it was so small, right? How often was it the case that it was so small? Does the model sometimes give us a random section with that poorly performing of students, I guess? Okay, we want to see how often that happens, and so that's going to take running this a bunch of times, because that's what our null hypothesis is telling us. So that's my last question for you for the day, I think. I'll do the rest for you. Try to simulate 10,000 averages into an array called sample averages. All right, so try to do that. You're going to run this function a bunch of times. Try to do it 10,000 times. You have a bunch of sample code now. We've done this a million times already in this chapter. Try to do that, please. Try to get 10,000 averages into an array. Call it that. And if you finish sooner than in my time, try to make a histogram. Try to get a p-value even, like how often was it that number? How often was it 13.6667? Or even smaller, right? Because if the randomness gave us a value that, or even smaller, even worse, then that would mean that the model actually does predict that. Like how often is the model predicting that value that small, or even worse? Because if that's unlikely, then that means it's a bad model. That means that there really was something else wrong. Maybe it was the TA's fault. Yeah, I'll give you a couple minutes to try that. Did I do that? I guess I did. Let me know if you have any questions as you're trying. how often was it that small? Or even smaller, because that would be alternative, right? I'll be leaning towards the alternative if it was even smaller than the value we really saw. So we didn't like that it was small. Could it have been worse due to chance? Or is that unlikely? All right, that is my timer. I think you know the drill at this point. Well, let's see. It's different for all of us when we rerun it, but it's gonna hover around the same kinds of things though. So let's see. Our graphs are gonna look very, very similar because we're doing it 10,000 times. So that's decently, like, the randomness will all, like, smooth itself away to look very similar for all of our different simulations. Let's see here. So I want to do, it's essentially all this all over again, right? Let me try and copy and paste. Instead of repetitions, I'll call it. It's also a simulation. You can think of it that way. So I'll call it simulations this time. Simulations, 10,000 of them. Do it. Simulations times, please. And I want to calculate not distances, but their sample averages. So sample averages is an empty array. Sample averages becomes one more with a new simulated average. Something like that. Does that make sense? That's how you can get that. And that will give us a sample averages array once it finishes. Pretty quick. And sometimes we got some small values, sometimes some big values, but I never see 13 in this example right here at least. But it could have been. So let's see how often was it so small, right? Because that's our claim, right? Maybe it was just due to chance that we just, like, that TA was given a bunch of bad students or something. That's what our null hypothesis is saying. Our alternative hypothesis is that average score was lower than we would expect from a random sample of students. Like, something was wrong. There's something other than randomness causing that low average. Maybe the TA was not teaching very well. Okay, so that is what we want to check. So we have this value, this 13.667 in section 3 average. We can deal with that in a second, but let's do a histogram of sample averages. So to do that, we better make a table with a column. Turn that array into a table with column random sample average. Sample averages, and then once I have that table, looks like that, nice. I'll call that something. I'll call it averages table for short. And we can make a histogram, averages table. Let's histogram it. By default, it's that, but that's a little spread out, so maybe we'll give it like 20 bins or something. Pretty. It looks like the score is hovering around. This is probably the true average of everybody. It's like 15, almost 16 out of the full score. So that looks like that is a decent average. And then we want to find where ours was. Like, where was the original section 3 average? It was 13.6 something. It was around here, right? Around there. And so it looks like sometimes, so just due to random chance, we were getting a score that was that low. Let's see how often. Let's calculate a p-value, all right? So what we want to do is here, let's add that dot as well. You don't have to know how to do this, but I'll do it for you. Let's dot scatter on the plot itself. That was section 3. The real section 3 average, color red, and then the size can be 120. So there's the one that we saw in real life, apparently. We got a value around there. And so we would like to calculate an observed significance level of p-value, which is the chance, based on our model, that our test statistic, which is just the average score of this random sample of students, was equal to the observed value, that low 13.667% in the sample, or even further in the direction that supports the alternative. So how often did our model predict a score that low or even lower? Does that make sense? That's what we'd like to calculate right now. How many times in our simulation did we do that? It looks like it happened at least a couple times, so let's see how often. So how often were we call them sample averages. How often were our sample averages less than or equal to this random not the random one, but the one we saw for the real original section 3. How often was it less than or equal to the 13 point whatever of the section 3 average? We can count how many times that happened, non-zero, count non-zero. That many times out of our number of simulations, which was 10,000. We can just divide by simulations if we change that. It's easy. And it looks like our model predicts that just due to random chance, about 5.8% of the time, just a section will be selected with a bunch of badly performing students, that you will just get a section with students performing that poorly due to random chance. Does that make sense, what we just discovered? So that's a number now associated with that idea. And in general, in real life, it's like when you calculate a p-value, it's like if it's less than or equal to 5%, then that's a statistically significant problem that you saw. Maybe that means we really should think about the alternative hypothesis. If it's less than 1, that means highly statistically significant. This is technically neither, right? It's not 5 or less, but it's super close to 5. So I guess the question of the day is now, like, if you were the instructor, what would you do if you were the teacher? Because it looks like it really is the case that 5.78% of the time, you really will get a section performing that badly just due to random chance. That's really close to 5, though. What would you do? I don't know. I guess you'd still, if I were the teacher, like, that would make me wake up, right? And say, oh, maybe that's too close to not being random chance for my eyes. So maybe I should pay more attention to this TA, give them, like, have somebody go observe them, make sure they're doing the right things. So yeah, even if it's not statistically significant, like, this number is still important. It looks like it's decently unlikely due to random chance, but sometimes it would happen. Just like you got a very unlucky TA with 27 students who didn't do too well, sadly. Okay, but that's how we can quantify it and make a decision. All right, that's what a p-value does. That's what these simulations do. It's like, due to random chance, maybe this happened. Let's see how often what we saw would actually end up happening if the model was true. Okay, if the null hypothesis, the thing that the model is predicting, happened to be true, what percentage of the time out of our 10,000 or so simulations that we want to do, how often is that going to happen? Okay, and I think that is the end of that story. That's a cute little one to end the day off with, I think. Are there any questions about that? Any questions about the things we did today? So we simulated some fun stuff, but it was always in the back of our minds. We had 2 hypotheses, right? We had a null hypothesis, some sort of model that we had in mind, like something was happening due to chance and just chance. We saw something that maybe was a little bit farther off than what we expected, but our null hypothesis was that, all right, that was just randomness, making it a little fuzzy for us. And the alternative that we were always considering in the back of our minds was the opposite. Like, okay, there's something else was going on. It wasn't just chance. It wasn't just random chance. The model really maybe wasn't a good model. Okay? But yeah, for our examples today, which is the opposite of last time, these models were bad models. It really wasn't the same as the population. But these models were good models, it looks like. Mendel, like, yeah, it was 75% chance. That's decent. That's predicted by the model. And then same with this one. It looks like the TA, maybe they just got unlucky. Like, the model does predict that with over a 5% chance of happening, that you just get unlucky and have a bunch of bad students or something. Okay? So yeah, I think that's where I want to stop for the day. Are there any last questions to have on the recording before I let you work? All right.